All right. Welcome. Good morning, Corey. You
Hello.
got your tie on. You're looking good. Did you say you work in a
Yep.
bank?
Yeah.
Yeah. All right. Well, I'm impressed that you're trying to watch this in your car. That can't be the best environment. So, all right. Let's count again. So we only had, I think, six. No, we had more than six, but eight. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's a little bit better. Okay. So today, oh, I could have sworn I had that open. We're going to be talking about 5.2, which is the trig form of complex numbers. Oh, I was sharing my screen. Can you see my screen?
I can see it.
Okay, good. All right, so we're going to talk about the trig form of complex numbers. So complex numbers can be graphed on an imaginary axis. So as we're looking here, you can see they've got IM for imaginary, and then we've got RE for real numbers. So we're going to graph the real part of the complex number on the x-axis, the imaginary part on the y-axis. And so as you can, if this is A, so if we've got a complex number A plus BI, this will be A, this will be B, and then of course your hypotenuse would be the square root of A squared plus B squared. So the absolute value of the complex number is the hypotenuse there, A squared plus square root of A squared plus B squared. Now, as we look at this, if we want to do this with trigonometric functions, your cosine is the adjacent over the hypotenuse, so A over R. Your sine is the opposite over the hypotenuse, B over R, and then your tangent is B over A. So we're going to make a definition. Any complex number can be written in the trig form as z, which is your complex number, z equals r times the cosine of theta plus I times the sine of theta. And a lot of times we will abbreviate that, since the thetas are the same, we will abbreviate that RCIS theta, R cis theta, where A equals R cosine theta, B equals R sine theta, R equals the hypotenuse, essentially, square root of A squared plus B squared, and tangent of theta equals B over A. Okay? So we can write, for example, Z equals negative 2 plus 2I in trig form. Okay? So if we're using our numbers here, so negative 2, that's going to be your x-axis. So we're going to go negative 2 in this direction. Let's write it as a negative here so it matches my picture. Negative 2 minus 2I is going to put us in quadrant 3. So we're going to be down here. So if I've got some complex number, negative 2 minus 2I, I'm in quadrant 3. So the hypotenuse, R, is just going to be the square root of 2 squared plus square root of 2 squared plus 2 squared equals 2 square roots of 2. Okay? So this length here is 2 square roots of 2. And to find your alpha, we just know that that's B over A now. So if I take negative 2 over negative 2, that's going to be a 45-degree angle. But as we can see from my graph, a 45-degree angle as measured from the x-axis is going to be a 225-degree angle because I am in quadrant 3. So, does that make sense? So what I could do is I could write this as R cis theta, and I can't copy that. R cis theta equals, in this case, 2 square roots of 2 CIS 225. Does that make sense? So I've just converted this to trig form. Okay. All right. Now we can also do it in reverse form. write 2CIS 120 degrees in standard form. Okay, so if we're drawing our graph here, I've got a 120 degree angle here. I know that my radius in this case is 2. R is 2, your hypotenuse, okay? I'm in quadrant 2. And so the idea here is 2CIS 120 can be written as 2 times the cosine of 120 and the sine of 120. So let's think about this for a minute. Now, most of us don't remember the cosine of 120, but we do know that the smaller angle here is 60 degrees. So the cosine of 60 is 1/2. However, because I'm in quadrant 2, I know that it's going to be a negative 1/2 because I'm in quadrant 2, because all students take calculus. So it's the sine is positive, but the cosine is negative. Okay, so the sine of 120, that's not one we remember, but we do remember the sine of 60. Sine of 60 is square root of 3/2. Once again, it's positive because I'm in quadrant 2. And so essentially what happens is this 2 will cancel out both of my denominator 2's, and I end up with -1 plus I square roots of 3. So, any questions there?
So how do you know if, so on that one you said that you knew it was in quadrant 2 because of the 2, right? The 2
Because of the
CIS
120 degrees. 120
okay.
degrees.
That makes sense.
That's what gave it away. Yeah. Okay. All right, now let's talk about the product of two complex numbers. So if Z1 represents a complex number and Z2 represents a complex number, so Z1 is going to be R1 times cosine theta 1 plus I sine theta 1, and Z2 represents R2 times cosine theta 2 plus I sine theta 2. We're going to FOIL this out. Now the nice thing is, you can think of R1 and R2. These are just scalars. We'll just pull them out front and together. So R1 times R2. Now we're going to FOIL out these two things here. Okay. So I'm going to have cosine theta 1 plus cosine theta 2 plus I cosine theta 1 sine theta 2 plus I sine 1 cosine theta 2 plus I squared sine 1 sine theta 2. Okay? We now remember that I squared is -1, so I can turn this into a minus sign here, basically. Okay? Now, if I rearrange things here, I'm gonna combine this with this. Okay, so the first term with the last term. Okay, but that's going to be a -1. Okay, so I'm going to still bring down my R1, R2, cosine theta 1, cosine theta 2 minus sine 1, sine 2, plus, and then I've got I sine theta 1, cosine theta 2, and cosine theta 1, sine theta 2. Now, does this look like any identities that you remember?
Yep.
Yep. It looks like the cosine of theta 1 plus theta 2. And does this look like an identity that you remember?
Yes.
Sure does. Looks like your sine of theta 1 plus theta 2. Okay. Now, since I've got these here, so I've got the cosine plus I sine, so I can rewrite that back as R1 CIS, R1 R2 CIS theta 1 plus theta 2. Okay. So the nice thing is, you just multiply your two scalars together, and then you add the two angles together, and you do a CIS of the two angles. Okay. So let's do an example here. Find the product of Z1 equals -1 plus I square roots of 3, and Z2 equals -3 plus I. We're going to use the trig form of the complex numbers, and we're going to write it in standard form, okay? So now let's look at this for a moment. Okay, so the first one here, okay? -1, so we're going to go in over here, -1 plus the I squareds of 3. So we're going to go the square root of 3 up here, okay? Now, if we're going 1 unit here, 1 squared plus square root of 3 squared is 3. So 3 plus 1 is 4. The square root of 4 is 2. So we know that our hypotenuse here is length 2. Okay? Does that make sense? I hope so. Somebody has to give me a verbal yes.
Can you just explain it one more time?
Okay. So we're just going to graph -1. So -1, 1 unit to the left. And we're going to go up the square root of 3 on the imaginary axis. Okay? So when I use my Pythagorean theorem, 1 squared is 1. Square root of 3 squared is 3. 3 plus 1 is 4. Square root of 4 is 2. So that I know that my radius here is going, or my hypotenuse here is going to be a length 2.
That makes sense.
Okay?
That makes sense.
Yeah. Question though.
Go ahead.
With the I in front of the square root, does that just tell you that it's imaginary number so you know where to graph it? Is that the whole purpose of that I?
Right, because
case?
we're graphing the imaginary on the y-axis.
Okay.
And we're graphing the real numbers on the x-axis.
Okay. Perfect.
Okay.
Thanks.
All right, we're going to do the same thing with z2, okay? So we're going to go out the square root of 3 in the x direction. We're going to go up 1 unit in the imaginary direction, okay? So z2, the square root of 3 plus I, okay? So once again, we're going to use the Pythagorean theorem. Square root of 3 squared is 3. 1 squared is 1. 3 plus 1 is 4. Square root of 4 is 2. So this one also has a length of 2. So both of these have a length of 2. Okay? All right, now, let's see here. So z1 is -1 plus I squareds of 3. Now, we can rewrite that. The radius is 2. Okay? Now, let's think about this for a minute. We've got 2 pi thirds. Now, why do we have cosine plus sine? Okay. Now, let's think about this. So if I've got this angle here is 2 pi thirds. Now, why is that angle 2 pi thirds? Well, we know we're in quadrant 2, right? We're in quadrant 2. The tangent of theta is going to be the square root of 3 over 1. And so we know that this angle here is pi thirds. Okay? If this angle here is pi thirds and we're in quadrant 2, we can figure out that that is 2 pi thirds. Does that make sense?
That makes sense to me.
Okay. If it doesn't make sense, slow me down. Okay. So, okay, so we can rewrite -1 plus I squareds of 3 as 2 CIS 2 pi thirds. Okay, now we're going to do the same thing with this other one. -3 plus, negative square root of 3 plus I. So we've got R is 2, as we talked about earlier, and we're going to write that as CIS 5 pi thirds. 5 pi 6. I need to fix my thing. 5 pi 6, okay? So we're at 5 pi 6 here. Now, how do we know we're at 5 pi 6? Okay.
The other side is pi 6.
The other side is going to be pi 6, okay? How do we know we're pi 6 here? Well, we can do the inverse tangent of B over A, opposite over adjacent. The opposite is 1 over the square root of 3, or the square root of 3 over 3. It's negative, so I'm in quadrant 2, and so if this angle here is pi 6, then this angle here is 5 pi 6. Okay? So this requires you to remember everything that we learned back on test number 1. Does that make sense?
Yep.
Okay. So I've just converted this to 2 CIS 2 pi thirds and this to 2 CIS 5 pi sixths. Okay? So what this means is we're going to take the 2's, we're going to multiply them together as 4. 2 times 2 is 4. CIS, now we just have to add these two angles together right here. 2 pi thirds plus 5 pi sixths equals 3 pi halves, okay? So we're adding these two together, now we're at 3 pi halves, okay? Cosine of 3 pi halves is 0. Sine of 3 pi halves is negative 1, excuse me. So this becomes negative I. So I've got 0 minus I, which is just negative I, and this becomes negative 4I.
How does it become 3 pi halves?
We're adding together 2 pi thirds plus 5 pi sixths. So this is 4 pi sixths plus 5 pi sixths is 9 pi sixths, which can be simplified to 3 pi halves.
Oh, gotcha. Okay.
Okay. Questions? There's mud. Okay. Nicole's like, yes, mud. That's a good word for it, right? All right. Okay. All right. So now we're going to find the quotient of two complex numbers. We are really moving fast. Okay. So if I take two complex numbers, z1 divided by z2, I'm going to write this as r1 cosine theta 1 plus I sine theta 1 over r2 cosine theta 2 plus I sine theta 2. Okay? Now, we're going to multiply by the conjugate of the denominator because we want to turn, it'll just make our life easier. So I've got r1 over r2. I'm going to pull that out. Cosine theta 2 plus I sine theta 2. The conjugate is cosine theta 2 minus I sine theta 2. So we'll multiply top and bottom by the conjugate of the denominator, okay? So on the denominator, that's going to give me the cosine of theta 2 squared minus I sine squared theta 2. I squared is negative 1. So that's going to become cosine squared plus sine squared, which equals what?
1.
1. So my denominator is eventually going to go away, okay? So that's going to be really nice. We've just turned the denominator into 1, okay? All right, now let's multiply my numerators together. Okay, so this is going to give me cosine theta 1 plus cosine theta 2 minus I cosine theta 1 sine theta 2 plus I sine theta 1 cosine theta 2 minus I squared sine theta 1 sine theta 2. So I squared is negative 1. That's going to turn this into a positive. I'm going to put it together with this one here because now it looks like an identity, right? So cosine theta 1, cosine theta 2 plus sine theta 1, sine theta 2 just becomes r cosine theta 1 plus theta 2.
Would it be
Then
minus
here, say it again.
cosine theta 1 minus theta 2? The identity for cosine is you use the opposite sign, right?
So this is just cosine theta 1 plus cosine theta 2.
I think you're getting mixed up
cosine theta
between
1.
sine and cosine, because sine is the opposite, And then cosine, I believe, is the same.
No, cosine's the
No,
opposite, sine's the same.
Sine is
Oh,
the
yeah,
same.
that's right.
On these,
Yeah, that's
So
right.
that should
Cosine of
be
yeah, it's opposite.
theta 1 minus
So then
theta
it should
2.
be cosine theta 1 minus theta 2.
Oh, so we've got this one, cosine theta 1 minus sine theta 2. Sorry, okay, you're right. I messed up. Yeah, so this, anyway, this is going to turn into here. This is going to turn into here. So I've got, cosine theta 1 plus theta 2 plus I sine theta 1 minus theta 2. And essentially that's, oh, wait. No, I want a
I
minus
see
here.
what you
You're
did.
right.
I get it
You are
because it
right.
was the cosine theta 1, cosine theta 2, sine theta 1, sine theta 2 is the identity for sine, right? No, never mind. You had it right. I'm getting confused.
Okay. All right. So at any rate, we've got cosine. So this turns into R1 CIS theta 1 minus theta 2. Okay. Does that make sense?
Can I, so I just need a refresher. Cosine squared theta 2 minus I squared sine theta 2. How does that get you a 1 again?
On the bottom?
The denominator, yeah. I just want to
So
make sure
I squared is
understand
-1. So this becomes cosine squared plus sine squared.
that. Oh,
So
plus
sine squared,
yeah.
this is the Pythagorean identity essentially, because that
Oh, okay,
becomes
okay.
a plus. In fact, maybe
Okay.
I'll put it as a plus here. So then it's easier.
Because it should be cosine squared theta, or cosine squared theta 2 plus sine squared theta 2, right?
Yeah, I forgot to do
Okay.
that. So
That's where I got a little confused. Okay, that makes sense then.
happened here. Oh, this is, I forgot. I have to use this stupid equation editor for this.
No, I don't think so. If you put in the 2, and then there's the x raised to the second power on the home screen, you can actually just click on that.
No, I can't. I got to use the stupid equation editor for this one.
Oh.
And in fact, I should have done that here too. All right. now it's perfect. Okay. All right. So okay. So nutshell, two complex numbers. The result is going to be R1 over R2 CIS theta 1 minus theta 2. Okay. All right, so example, we're going to find the quotient of -1 plus I and the quotient of -3 minus I by using the form of trig complex numbers. Okay. Now let's graph, and I swear I can't do these without graphing them. So -1 plus I. So I'm going to go -1 plus I, that's going to be your Z1, okay? Now, let's talk about the length of your R here. So I've got 1 squared is 1, 1 squared is 1. So this is going to be the square root of 2, okay? Now it's probably pretty easy to see this is a 45-degree angle if this is 1 and 1, right? Okay. And so if this is a 45-degree angle and I'm in quadrant 2, theta 1 is going to be a 135-degree angle. Does that make sense? Okay. So I can rewrite -1 plus I as square root of 2 CIS 135 degrees. Okay. We'll do the same thing with our Z2. Okay. Z2 is -3 minus I. So if we're going to go, it's the square root of 3 minus I. So we're going to go square root of 3 in this direction. We're going to go down 1. So square root of 3 minus I. So square root of 3 squared is 3. 1 squared is 1. So 3 plus 1 is 4. Square root of 4 is 2. So this length here is going to be 2. Okay. Now we've got to get our thing here. So I've got the square root of 1 over the square root of 3, which is the same thing as square root of 3 over 3. So that's going to make this a 30-degree angle, but I'm in quadrant 4. So 360 minus 30 is going to be 330 degrees. Okay. So theta, I should call that theta 2 to be careful here. So theta 2 is going to be 330 degrees. Okay. Everybody with me so far?
So how do you know? Because you said that. So can you just go over how you found that 330?
Yeah. Okay, so this angle here is going to be so we know it's going to be the inverse tangent of the opposite over the adjacent. Well, the opposite is 1. The adjacent is square root of 3. 1 divided by the square root of 3 is the same thing as square root of 3 over the square root of 3. Okay, so the inverse tangent is square root of 3 over square root of 3. That only happens if this acute angle is 30 degrees. Are you with me, Graham? Do you agree that this is 30 degrees?
Yeah, yep.
Okay, because this is 30 degrees, if we measure it from here, then it becomes 330 degrees because I'm in quadrant 4.
Right. So I guess what I was confused about is why do you use the tangent for that one?
Because I've got the two sides.
Okay.
I know that the adjacent side is square root of 3, and then the opposite side is 1.
And that's because based off what we know, the first term is x, the second term is y.
Correct. You can think of it that way.
Okay. Perfect. Thank you. That's what I was confused about.
Yeah, and we kind of talked about that at the very beginning. Tangent is just b over a. So it's going to be your imaginary component over your real component. Okay. All right. Now, okay. So we've just converted these to trigonometric form. So it's going to be the square root of 2 CIS 135 over 2 CIS 330. So I'll just do the scalars together. It's square root of 2 over 2 times CIS, and then we get to subtract 135 minus 330 degrees, which works out to be negative 195 degrees. That's not one that we know, so we're going to have to plug that into our calculators. We're going to get square root of 2 over 2 times the cosine of negative 195 degrees, and as everybody knows, that's negative 9.983 plus I sine of 195 degrees, and as everybody knows, when you plug it in your calculator, that works out to be 0.183 times I. So, yeah, this is one you couldn't really do without your calculator. So, gosh, that was really fast.
Where did the square root 2 over 2 go in that answer?
So the square root of 2 over 2 is outside. So if I find the cosine of 195 and then I multiply it by the square root of 2 over 2, that gives me negative 0.983.
Oh, gotcha. Okay.
And then the sine of 195 degrees times the square root of 2 over 2 is 0.183.
Okay, cool. Thank you.
Okay. All right, hey, let's talk calendar for a moment because we're done with 5.2. Let me pull up my calendar and show you what I had planned to do because we got done really early today. Okay, so here was my calendar for the rest of class. Now, I was only planning on covering 5.2 today, but we did that so fast. We could cover 5.3 if you want. Now, we'll talk about the pros and cons. We can end class today because I was only planning on covering 5.2 today, but we're done so early. And then we were going to do 5.3 tomorrow, which was de Moivre's theorem. And then we could move 6.5 up to Tuesday if we covered de Moivre's theorem today. Okay. Now, the benefit of that is basically we can cover everything for exam 3. So exam 3 will cover basically 4.1 to possibly 6.5. We'd still have a review day on Wednesday, but you'd be fully tested on everything. Okay. Then we could just have a review all next week and have our final exam on Thursday. So, or if you want, we can stop today. We can do 5.3 tomorrow. We can do our review Wednesday like we were planning. Then we would only have one section that's new for the final, have 2 review days. So here's what I will do. We'll do a vote here. Let's go to the chat. So who wants to cover 5.3 today and cover 5.3 tomorrow, which means we're done with class today? So you can just give me a thumbs up. Of course, you have to be signed in to do the thumbs up. Y'all are procrastinators, huh?
Well, hey guys, if we cover 5.3 today, that gives us more time to review for the final. And the final is going to cover a lot of information.
But that also means that we have 2 quizzes tonight and 2 homeworks tonight.
That is true.
Yeah.
I don't know about you, but I don't have time for that.
Yeah.
What do you mean? We got lots of time.
To go over the assignments in class, but not to do homework and quizzes.
All right. Okay, so y'all want to be done today, looks like. Okay. Well, because we got done really fast today. Okay, well, then I get earlier starting writing the quiz. So, and then I get to go to the Jazz game. Did I tell you guys I work for the Utah Jazz?
What do you do with them?
So that little scoreboard you see in the bottom of your screen, I run that.
What?
That's cool.
So obviously I'm not in Orlando. I'm here. It's really weird what they're doing because at first, here, I'm going to stop recording, but if you guys want to hear or if you want to drop off, I don't care. But let's see, stop recording. That's what I meant to do.